The buck converter has three important components to be designed or rated. One is the single pole double throw switch, the other one is the inductor, and the third component is the capacitance. Now let us take one by one. Let us take the inductor. So inductor L value. How to find the value of L? We will use the Faraday equation. VL is equal to L delta IL by delta T, L DIL by dt. Now we see that in the inductor current waveform, it is a straight line linear because the rate is constant. So therefore I can take it as delta IL by delta T, and delta T is nothing but dTs here, or 1 minus dTs, depending upon which period you want to take. So let us say I am talking of dTs period. So in the dTs period, the slope is the current traverses through delta IL, that is this, in a period of dTs. So for that, the voltage that is seen across the inductance is Vi minus V0, which we will put it down. Other way, I can look at the other portion, 1 minus dTs portion also. So L delta IL, the current traverses through delta IL in time 1 minus dTs, and during that the magnitude of the voltage is V0. You can put only the magnitude, which is V0, because the traversal is negative. You can put negative V0, negative can be removed, and you have V0. So either I can use this equation or this equation, because let us say, for example, Vi can be expressed in terms of V0 as V0 by D. Substitute here and you will get all in terms of V0. So the value of L is V0 into 1 minus D. Ts, I'll bring it down, call it Fs, switching frequency, delta IL, switching frequency. Now this is the basis for the design equation for L value. V0 is a design spec given for you based on the output load side spec. D is designed from Vi and V0, both are specs, and therefore D is calculatable. Fs is the switching frequency. The designer chooses whether you want to switch at 20 kHz, 50 kHz, 100 kHz. Then delta IL again is a designer spec, and normally it is taken as 10% of I0, max I0. So with this you can get the value of L. Let us now obtain the capacitor design equation. So capacitor C. So the capacitor current is the important waveform parameter that we have to look at. Just like in the case of the inductor design, we looked at the inductor voltage across the inductor. Here we will look at the capacitor current. So let us remove some parts of the waveform, focus on the capacitor current. Now let me shade this. This is the area under the capacitor current curve on the top, and this is the change in the charge. We'll call that one as delta Q. So the change in the charge, that is, this is charge up, and the area here would be charge down, discharge. So the charge up and the discharge should be equal and should cancel out for amp second to balance. So delta Q we know is equal to C into delta V, change in the voltage across the capacitance. So let us try to find what this area is. This area is nothing, this is a triangle, therefore half base into height. Now let us find out the height. Height is the distance between these two from 0 to the peak of the triangle, and that we know is delta IL by 2. Because this whole height from here to here is delta IL. So this is delta IL by 2. And what is the base of the triangle? So that is the distance from here to here. So what is this distance? So here if you see that this is from minus delta L by 2 to plus delta L by 2. Now this is linear, therefore this has to be the midpoint. So therefore this must be dTs by 2. So this is dTs by 2. Likewise, this is the midpoint in the 1 minus dTs portion. So therefore you have 1 minus dTs by 2. So together you add up dTs by 2 plus 1 minus dTs by 2, which will be Ts by 2. So this is Ts by 2 irrespective of the value of the duty cycle. This is Ts by 2, which is the base. So now you can calculate the charge, which is half base into height. So half base Ts by 2 into height delta L by 2, and that should be equal to C into delta V. Now C, let us calculate C is delta IL divided by Ts. I'll take it down as Fs, switching frequency. This 2 into 2 into 2 is 8. Fs delta V comes down, that is the ripple across the output. So this is the design equation for basis of the design equation for C. Delta IL design parameter while designing VL, we took it as 10% of the max I0. Fs switching frequency, we know what switching frequency we are designing for. Delta V, the output voltage ripple due to capacitor action is output spec. So we know that. So based on that, we can calculate what should be the value of C. Of course, in a practical capacitor, there will be ESR. Drop across ESR also will come into the ripple. But anyway, we take here the ripple across the capacitor due to the capacitor action, which is equal to I is equal to C dVc by dt. Now let us look at how we will implement this single pole double throw switch. Of course, it cannot be implemented by a single semiconductor device. It needs at least 2 semiconductor devices. And let us see how we select the appropriate semiconductor device for the appropriate throw. So let us make some space here. Now consider, for example, a single pole single throw switch. A single pole single throw switch like this, like that of a relay contacts. How is its IV static characteristics? So draw the V versus I. So V is the voltage across the SPST switch and I is the current through the switch. So now let us say that this is throw and this is the pole, and let us say that positive direction is current flow from throw to pole. Now does this switch allow positive direction current flow? Yes. So therefore we will mark this like this. Will it allow current to flow from pole to throw? The SPST switch, like the relay contact, will definitely allow. So which means this is also a potential operating point. Now coming to the voltage, can throw to pole support a voltage with throw as positive and pole as negative? When the switch is off, can the voltage that needs to be supported by the switch be positive like this, throw positive, pole negative? Yes, in this case this is possible. Therefore you can say that these are possible operating points. Likewise, we can also find out whether the switch can sustain voltage in the negative direction. Yes, so this also becomes an operating point. So for the SPST switch static IV characteristic, the entire y-axis, current axis, and the entire voltage axis are operating points, which means the switch can support positive voltage during the off condition, it can support negative voltage during the off condition, and during the on condition it can support positive direction current flow, it can support negative direction current flow. Now take for example another switch at diode. Diode is a switch with the anode, cathode like this. So how is it static IV characteristic as a switch? So now let us consider, does this device allow current flow from anode to cathode? Yes. So that if we call as positive direction, then we say this is the set of operating points. Will it allow negative direction of current flow, that is from cathode to anode? No, that will not be allowed by this device. Therefore, there are no operating points in the negative axis of I. Will the device, the diode, support voltage from cathode to anode? Yes, but cathode to anode is the negative voltage. Yes. Can it support positive voltage and anode to cathode, during which time it will be forward biased? No, therefore there is no operating point in the positive direction of the voltage axis. So this means that diode can have operating points on these marked segments where it can support negative voltage when it is off, and when it is on it can support positive current to flow through it, which is anode to cathode. Take for example another semiconductor switch like the BJT or a MOSFET. So you have the collector, base, emitter, gate, drain and source. So how do the IV static characteristic for switch appear like if these two are operating as switches? So when they are on, does these devices allow current to flow from collector to emitter if we consider that as positive direction, drain to source if we consider that as positive direction, then yes, all these are operating points. Does it allow emitter to collector current flow or source to drain current flow? No. So therefore the negative portion of the I-axis are not operating points. Likewise, now for the voltage, can a positive voltage collector to emitter be supported by the BJT during off condition, or a drain to source voltage, positive drain to source voltage be supported by the MOSFET during the off condition? Yes, it can do that. Therefore, all these are potential operating points. On the other hand, the negative voltage for both BJT and MOSFET cannot be supported by these, and therefore the negative axis cannot be operating points. This indicates that during off condition, this device can support only positive voltage, and during on condition, it can support only positive current. Now, with this background, let us get back to our buck converter single pole double throw switch. Now there are two throws, T1 and T2. PT1 is one semiconductor switch, PT2 is another semiconductor switch. So let us take one static characteristic for PT1. So we will call this voltage T1P. I am taking T1 as the first node, P as the second node, I T1P. So the positive direction of current flow is T1 to P, and positive for the voltage support is T more positive than P. Likewise for T2P, I am taking V T2P throw to pole and I throw to pole. Now let us see how these characteristics get filled up, and then we will map them to the available device. Now take for example PT1. In the case of the PT1, you can see the current through T1P. The current through T1P is positive, only positive. There are no negative direction currents. So all the currents that flow through the T1P is positive. And if we go back to this page, you will see that the positive axis of current are all possible operating points, because the current in this pole throw switch is always positive. Likewise, the current through the throw to pole T2 to P is always positive. Observe that T2 to P, the current flow is always positive. So here too, you will see that the possible potential operating points lie on the positive current axis. Likewise, when you talk of the voltage supporting, when PT1 is off, T1 is more positive than P, because when T1 is off, P is connected to ground, so T1 is more positive than P. So only the positive side of the voltage axis are potential operating points for PT1. And in the case of PT2, P is more positive than T2. T2 is grounded, zero potential. P is either 0 or Vi. So when PT2 is off, P is connected to Vi, positive potential. Therefore, T2P is negative. So only the negative portion of the axis are possible operating points. So from this set of requirements of the switch IV, we can say that this matches with the BJT or MOSFET or IGBT type of IV switch characteristic. So we can choose a BJT or MOSFET for PT1 switch or even an IGBT, and this matches with the characteristic of a diode. So therefore we can say diode is the best suited for T2P. So we can place a diode somewhere like this here, and we can place a BJT or a MOSFET or an IGBT in the T1P place, and these two together will form the single pole double throw switch, the equivalent function. So let us place these components in place of this single pole double throw switch and see how the circuit will look like. So let us erase those portions. We will place the BJT here in this direction, T1 to P. This is the pole. Diode in this direction. This is the pole. This is Q and this is D. So this is the buck converter circuit with the semiconductor switches in place. So when this Q1 is made on, you will see that the current flows in that direction, charges up the inductor and then back. And when you switch off Q1, the inductor current will pass through this and this and freewheel through the diode automatically, and the energy will start discharging, and therefore the falling slope in the current. So this is how the switches are selected for a converter, for any general converter. Now let us look at the waveforms. Let us see how we will rate Q and D. Now Q is T1P. So T1P, the voltage VT1P. Look at this. When this Q is on, it carries current IT1P, this one. When the Q is off, the voltage is withstanding capability should be at least Vi. Vi comes across this. So therefore, if we take Q1, the VCEO rating for Q1 should be greater than Vi. So it should be greater than this height, and Vi max, because this is unregulated, this can swing from Vi min to Vi max. It should be able to withstand Vi max. The current rating, current max rating flowing through this BJT or MOSFET should be capable of withstanding this much. So it should be greater than I0 plus delta IL by 2. Likewise for the diode, the peak inverse voltage rating for the diode, the negative voltage that the diode should be able to withstand is PT2, and this is Vi, and therefore should be greater than Vi max. And the current IDM, max current, that flows through the diode is here shown here, T2P, and this again is I0 plus delta IL by 2. Therefore IDM should be greater than I0 plus delta IL by 2. Other currents like average and RMS currents can be easily calculated from this wave shape, and thereby we get the ratings of the two semiconductor switches. So now we know how to calculate the value of L, how to calculate the value of C, how to choose the semiconductor switch and the semiconductor switch ratings Q and D for the buck converter.